All right, good morning, everyone. Welcome to Advanced Kentucky's third AP Calculus AAB content review session. My name is Aaron Simmons. I'm the Mathematics Content Director for Advanced Kentucky. We are lucky to be joined today by Mr. Mark Crawley from Ryan High School in Denton, Texas. So before we get started, we're going to go over just a couple intro slides. Please make sure you are accessing today's handouts at bit.ly/mathcrs, which you see on the screen. So this online review session is intended for a Kentucky audience, but I know that we have lots of teachers and students from around the nation. So welcome. We will do everything we can to make this as engaging as possible. Please know that any participant that's causing disruption will be removed. And also AP is a trademark registered by the College Board. They are not affiliated with and do not endorse this product. Our contact information here for Advanced Kentucky is on the screen. Give us a follow, look us up on Facebook. My email is right there as well if you have any questions following up on today's session. Today, your microphones and videos will remain off, but your chat is on. So please, please, please ask any and all questions. You can direct them directly to myself. You can put them in the chat to everyone. You can put them to Mark. We will make sure we address all questions in due process. So please make sure that you are using the chat. We want to make this as beneficial to everyone as possible. And then for those of you that may also want to know about past review sessions or upcoming ones, a recording of today's session will be posted to the bit.ly/advky website shortly after the session ends. So it'll be up by the end of the day, most likely. You can also see links to handouts there. You can see past recordings. If you are a teacher and you have students that are in the BC session or you want to see the BC videos, you can go back and look at those as well. And you can see a schedule of our upcoming sessions as well. So with that said, I'm going to turn things over to Mark and he can introduce himself. I'm sure most of you are familiar with him already, but he can give you a once over on himself. Mark, take it away.
Hi, yes, I am Mark. And I worked with College Board for the AP Live videos last spring and the AP Daily videos. I was in Unit 1 and Unit 8, and I was the lead instructor for those. So if you find mistakes, you can actually reach out to me and we can try to get those fixed. And then just to let you guys know, we are doing review sessions with AP Live again, the 2 weeks leading into the first administration of the exam. So April 19th and April 26th. And it's going to be Verge, Cornelius, and myself again. And Verge is actually doing your next review session here for the ABM. Couple of things I just want to piggyback on some of this, the ground rules that Aaron said. Please, I know he's your voice because you're muted, but if you have a question, please interrupt. I run this like I run my classroom, hopefully, which is I go as fast as you let me. So if there's something I say and I think it's a throwaway line and you're like, wait, what was that? Throw it in the chat. If I don't see it, Aaron will see it. He can interrupt me. But we're here to help you guys get as much as we can during this time. I really wish we were all in person and I could walk around the room and see how you guys are doing, but I can't. So I need input from you guys to help me with that. So let me go ahead and start my slideshow and start the share. You'll have to bear with me on the tech side. There we go. All right, and can you see the slideshow now? I'm looking at, see, what are you seeing the slideshow or are you seeing?
Sorry, we can see your the first slide.
Okay. Yep, that's the one you should be seeing. Okay, good. All right, so this is just our agenda for today. We will have an hour, or we won't have an hour break. At the 1 hour mark, we will have a little break. And we're going to do a couple warm-ups. We're going to start with multiple choice. When I was trying to decide how to do this, because this is the first one I've done was really a student-led version is what I would call this. And so I'm trying to get my chat up. As soon as you share, the screen rearranges. So, all right. As I was trying to develop what I wanted to do with you guys, I decided that I would focus on free response for 1 hour and multiple choice for the other. So our warm-up is going to be multiple choice, and then I'm going to focus on free response through this first hour, and then we kind of flip it in the next one. So our warm-up is actually going to be in this one, just these 3 little open-ended questions. It's really hard for me to be silent, but I'm going to try and be quiet for a minute or two and let you take a chance to answer these. And is this the wrong slideshow? I opened the wrong slideshow. I did that when we were starting to. So don't worry about that warm up. And slideshow. Can you edit this out of the recording?
It's gonna look choppy, but we can.
Here we go. Here's our warm up getting started for 5.5 and 5.9. So the warm up for these are going to be multiple choice, and then we're going to focus on the free response. So you're given the graph of G prime, the derivative of G, it's shown to the left, and which of the following could be the graph of G? And we're just trying to connect derivatives today. This should be a carryover from your last sessions. Aaron has put the link in the chat, and these are all in the handout in the chat as well. There's a doc that you can look at. Give you about 15 more seconds because this one's a pretty quick inspection one, and then I'm going to move to the next question. All right. And I know people are still entering, but we'll come back and read through these. So this is our second warm-up question. This one is a multiple choice. You know, there's a wall of text on the screen right now, but it says, on a certain day, the total number of Snapchats a high school student takes is modeled by S, a differentiable function of the number of hours since the student woke up. Which of the following is the best interpretation of S prime of 7 equals 20? You have the choice, the student has taken 20 snapshots an hour, 7 hours after waking up. Choice B, the student takes 20 snapshots the first 7 hours after waking up. Choice C, the rate the student is taking snapshots is 20 snapshots per hour, 7 hours after waking up. Or D, the rate of the student is taking snapshots is increasing at a rate of 20 snapshots per hour, 7 hours after waking up. Give you a little bit more time. If you have a piece of scrap paper, go ahead and write down an answer. Just commit to it so you have a little emotional tie to it. And we're going to do our third warm up. This one, you have the graph of f is given. It says the graph of the function f is shown above for -2 for this interval from -2 to 4 for x. Let g be the function defined as g of x is the integral from 0 to x of f of t dt. On what open interval is g increasing and concave down? You have some choices there. I'll give you a full minute on this one. It'll take some time to interpret it. I'm going to go ahead. I know we still had some people coming in, so I'm going to go ahead and show the first two again real quick. Just give people a chance to look at those. So the first one, this one should be a pretty quick read for you. It's just, here's a graph of a derivative on the left, and which of the following could be the function that is the derivative of. And the second one is the Snapchat question. S prime of 7 is 20. And S is the number of Snapchats a student takes since then, as a function of the number of hours since the student woke up. All right. And Aaron has set up a poll. So you want to go back to the first one? Can you set up that poll?
We're ready. All right.
All right.
So just, I guess we'll just go A, B, C, D from left
Yeah,
to right.
yeah, we'll just call those A, B, C, D. That seems to make sense, right? So,
right.
Whoops.
If you need to move that window out of the way, you can to see the question again. But once we get this put in, we will end the poll and display the results.
So that's fun watching the live.
Yeah. So, again, these are anonymous, so you please respond.
Yeah, don't feel peer pressure to join others, right?
All right, 15 more seconds and we'll display the results.
There's definitely 2 in the lead, huh?
All right, we hit 68%. Here are the results.
All right, so I don't want to close that one. I scoot it away. All right.
Yeah.
So what I'm looking at with this is my derivative. So for G prime, here's my 0 right there. I'm looking at negative for the entire left. I've got some positive, some negative, and some positive. So when I think about what G is doing, actually I might change colors for that. If I can get my pen to actually work for me. There we go. So G is going to be decreasing. It's going to be increasing, decreasing, and then increasing. And so the choice A is not a bad choice because we do have that decreasing the entire time. However, we do start decreasing slow and then picking up. So that should be getting more negative the entire time. And then on the right, it's increasing the entire time, which unfortunately does not work with our situation here. B is a very awkward looking graph, but it does have this decreasing the entire time, increasing, decreasing, increasing. That one looks highly likely. And then as we look at C and D, we have increasing on both sides in the left quadrants. So it is in fact choice B. And forgive my handwriting on the electronics, but I hope that makes sense. And no questions in the chat over that, or okay?
Not on my end, no.
Okay, so let's go ahead and look at B. You want to set up the poll for that one? By the way, the source of these problems, I actually had teachers write these at a workshop. So these are all based on previous AP. They're based on one of the practice exams that have been released, but they're problems that have not been actually used by College Board. So I'm not stealing anything. So about 15 more seconds.
Sounds good to me.
All right. So I'm actually going to go through these. C was the popular choice, and I believe you guys did well. The first one is actually the slope. If we look at that first one, it's This is because it's the oops, jeez. My pen doesn't want to be a pen right now. There we go. So that 20 snapshots an hour for the 7 hours, it's this has taken, it loses the instantaneous. And so that feels much more like S of 7 minus S of 0, the number of pictures taken over the interval. So that's not going to work. B sounds like how many they took. So that sounds like S of 7. C, we have rate, which we definitely want. It's got this more of an instantaneous. It is taking 7 hours after waking up and that rate of 20 snapshots per hour. So that does feel like S prime of 7. And then D, the thing about D is whenever you see the phrase is increasing, look at what is increasing and it's the derivative of that. So this would be the second derivative because they're talking about the rate actually increasing. So they're talking about the rate of the rate. So C was correct. Good job on that one, crowd. We crowdsourced that one well. And D is number 3, I guess here. Oops. I said D, but it's not actually, I don't think that's actually the right answer. Don't want to like bias people. This one actually has foreshadowing for the next hour, right? Like this has got a fundamental theorem sneaking into it. I'll give you about 20 seconds. While you do that, I'm going to say the first hour and the second hour are going to be a little different. The first hour, I'm kind of going with the assumption you guys have all been through derivative relationships for a while. So it is going to be more like this. We're just going to look at problems and talk about strategies. I'm going to do a little more instruction when we get to unit 6 because it's kind of fresher and a little more disjoint. All right, that was our minute. We got a lot of choices for B here, 60% for B. So what I'm looking at is we've got, if I get make sure my pen's turned on this time. Nope. Yeah. PowerPoint is not being my friend. So G prime is f of x by the fundamental theorem of calculus. That's the derivative version of the fundamental theorem of calculus. Some books refer to it as part 2, some books refer to it as part 1. But no matter how if you take the derivative of the left, you get the f of x on the right. So we're looking for where G is increasing. So we want G prime to be positive, and G prime is F. So the only candidates right now are those left and right ends, because that's where G prime is going to be positive. And then the second part, is there bringing my highlighter on accident? My second part is this concave down. When I want to talk about that concave down, it's going to be G double prime. So I want to look at, is F prime increasing or decreasing? So concave down, we want this to be less than 0. So I'm looking through this interval. And so the overlap is that -2 to -1. And indeed, B was the correct answer because that's where my G prime is positive and my G double prime is negative. So good job, guys. All right, we're going to move on to some free response. These are actually problems I wrote myself. Don't be overwhelmed by the text. I'm going to read the whole text to you, and then we're going to do one part at a time. This is actually based on 2 different past AP questions. And at the end of this presentation, I actually give you links to a couple real AP problems that have been released that you can practice on and look at the scoring guidelines that are very similar. So we have a differential equation, dy dx equals 3x minus 2y squared. And in part A, we're just to find the second derivative in terms of x and y. In part B, let y equal f of x be the particular solution to the given differential equation, whose graph passes through the point 6,3. Does the graph have a relative minimum, relative maximum, or neither at the point 6,3, and justify? Then in C, we say let y equal g of x be the particular solution to the given differential equation, whose graph passes through the point 2,1. So we now have a different solution for the same differential equation. says use the tangent line through the point 2, 1 to estimate g of 2.1. And then D, this question's phrased a little differently because I kind of merged some AP questions. It says, do you suspect C is an underestimate or overestimate? On a real exam, you'll have enough information to make that call and then explain your reasoning. So I know we're tight on time and I don't have the ability to walk around the room, which is really depressing for me. But what I want to do is just give you 30 seconds. If you want to get started on the problem, that'd be great. If you can get through it, some of you will be sharp enough to get through it. And if you don't, if you just need to jot down a strategy, if you don't, in 30 seconds is not enough time to do it, which is perfectly fair. At least write down something like, this is what I would do. And then we can confirm whether that was correct or not. So like I said, I'm gonna give you about 30 seconds to work on this part A. All right. And can you see my, sorry, I've covered up Aaron, so I can't even get a facial cover. Can you see my camera now, my dot cam?
Yeah, it looks good.
Okay. This is just because my handwriting on digital is kind of sketchy, so it's just easier for me to bring in the dot cam. So, all right. So this notation, hopefully you're familiar with that, but that's the second derivative. That's why we have two D's there. So we're taking the derivative of y again with respect to x both times. And right here we have the derivative of y with respect to x. So I'm going to go ahead and just left side state what I'm doing. The derivative of 3x is 3. Whenever you're dealing with multivariable equations, which is what this is, because it has the x and the y, I think you should always check, what am I taking the derivative with respect to? It's x. What did I just take the derivative with respect to? X. So 3 is my derivative. Then I'm going to take the derivative of this 2y squared term. So I drop that 2 down. 2 times 2 is 4. Subtract 1, I get 4y. Again, taking the derivative with respect to x, this is not an x, this is a y. So we get that implicit chain rule of dy dx that pops out. And now this is my derivative. I look back at what I was asked to do, and it says in terms of x and y. It's only in terms of y here. If x goes to a constant, that's fine. I'm not concerned about the fact that there's no x. I don't have to force an x in. But I do have this dy dx, and so I need to reinterpret that. But I have right here that dy dx is 3x minus 2y squared. So my second derivative is 3 minus 4y times this 3x squared minus 2y squared. Sorry, I read that wrong because I read it as a writing and reading at the same time are not always the best plan. 3 minus 4y times 3x squared minus 2y squared. And you can leave it like that. You can simplify it, or you can just stop. As soon as I've satisfied the conditions on a free response, I have my second derivative. It is in terms of just x's and y's. I can walk away. And I would recommend that if you have any type of problems with distributing. And honestly, myself, I'm kind of afraid I'd screw up the -4 times -2. So now your teacher's rules may vary. So in your own classroom, your instructor or your college professor next year or in a couple of years might actually require you to simplify that. But for the rules of the AP exam, we get to move on. All right, so now I'll give you a little time with part B. Now we have dy dx, same dy dx, and going to ask, you cannot find the particular solution to this with calculus AB and calculus BC content. So let y equal f(x) be the particular solution to that given differential equation. And does the graph have a minimum, maximum, or neither?
Oh, and Mark, I think you put an extra squared on the x in your parentheses there.
Oh, I sure did. Thank you. That's why we need active people coming in. Thank you.
Thanks, Sarah, for that.
The good news is if I did carry that in on the AP exam, they'd let me get part B. That would have been a copier. I would have been able to at least recover in B. I also don't think it would have changed the answer, but that's kind of fun. All right. Yeah, I know time is kind of a luxury that we don't have, so I'm going to jump in here. So when we look for minimums, maximums, relative min, relative max, or neither, relative mins and relative maximums always occur at critical numbers. So we need to decide if we have a critical number or not. So the first thing I'm looking for is this. Is this a critical point? So I'm going to take 6(3), and critical numbers are where my first derivative is 0 or undefined. So I'm going to take dy dx, and I'm going to type in, or plug in 3 times 6 minus 2 times 3 squared. That is 18 minus 2 times 9, which is indeed 0. So we have a critical number. So we at least have a candidate for minimum or maximum. Now, if the first derivative was just in terms of x, I could try to do a first derivative test. I could scoot a little to the left or a little to the right and see if my derivative changes sign. Unfortunately, while I know 5 and 7 are left and right of 6, without doing a lot of analysis, I'm not sure what y would be doing at 5 and 7. I might suspect I might be able to plug in, but there's just 2 variables going on and it takes a lot more work. I've seen first derivative tests written up for problems like this. It's about 2/3 of a page typed as an explanation. So you don't want to go that route on the AP exam. You don't have that kind of time. So this is a case where we actually are going to use the second derivative test. Because we have a critical point, and that's one of the conditions for our second derivative test, is we need a first derivative equal to 0. It can't be undefined because then the second derivative is not going to exist. And I need to have a second derivative, which I do. So I'm going to take my second derivative, this d squared y dx squared, and I'm going to evaluate that at the point 6(3). So 3 minus 4 times 3. Now I could plug in here and do 3 times 6 minus 2 times 3 squared, but I actually know what that is, right? That's this first derivative. So that's going to be the 0. I could actually plug into this version, but almost be more useful because I know dy dx is 0 right now and y is 3. And that is going to be 3 minus 0, which is going to be greater than 0. Actually, I think it might have changed the answer with that now that I think about it. If I'd left that x squared there. Good thing we didn't. You said that was Sarah? So, so we have second derivative greater than 0. That's actually enough at that point. With those 2 conditions, with the second derivative test, with a critical number of 0 and a second derivative positive, I can just state what this is. But I tend to be more visual, so I'm going to kind of do this thought bubble of this is a concave up curve, and I'm at the horizontal tangent on it. So there is a relative minimum at the point 6(3). And I hope that makes sense, okay? But this is when students ask me a lot of times, why do we have to do the second derivative test? It's for implicitly defined functions a lot of times. There's a couple other great uses for it, but this is one of those really obvious where first derivative test just is a lot harder to pull off. And now we're kind of leaving and doing a new problem because now we're leaving f of x and talking about g of x. This is let y equals g of x be the particular solution. And now we're going to pass through the point 2, 1. And we're going to use the tangent line through the point 2, 1 to estimate g of 2.1. And yeah, I know you guys don't necessarily have time to look at all of those great resources that are on the internet, but just a little plug for the Advanced Placement YouTube channel. If you go to youtube.com/advanced placement, all of our review videos that we did for AP Live last spring when the pandemic hit are online. And we did all of Unit 7 and Unit 8, and we touched Unit 8, but we did all of Unit 7 in there. But if you have gone and watched any of those, you know that every time we do a tangent line, my goal is to get my voice into my kids' heads during the test. And when I see a tangent line problem, the first thing I want is, what do I need to find a tangent line? And I need a slope and a point. So I'm going to give you a couple seconds to try to get that tangent line. All right. So the point's easy. They gave us the point. We know the point's 2, 1. To get my slope, well, I need a formula for my slope, and fortunately, dy dx is the slope of the tangent line at a given point. So I'm going to evaluate dy dx at 2, 1. By the way, I use this such that notation. This bar is a such that from set notation, or an evaluation bar. You see it with the antiderivative as well. I use this notation just to specify where I'm plugging 2, 1. You do not have to use this notation on the exam. I don't want anyone thinking that you're going to lose points if you don't do that. I'm going to do 3 times 2 minus 2 times 1 squared. That looks like 6 minus 2, which is 4. So my slope is 4. Point slope form is the way to go. Many of you probably learned point slope like this. Oh, thank you for that video, the video link. I prefer this form. It's actually called the Taylor form for the BC kids. But I like having the y1 over there already. But we're going to plug in our point 2, 1. So 1 for y, 4 for my slope, and x minus 2 inside. And so that's my tangent line. And then they want me to use that tangent line to approximate g of 2.1. So I'm going to plug in 2.1 for my 2. Again, I'm trying to be as mathematically correct as I can because that's what I should do best for you. If you write in equals here, if you plug it in with the y equals, it's fine. You've been asked to estimate it and you're stating your estimate equals that. That's fine. I'm just putting the squiggles because it's what I've been trained to do. And so our estimate of g of 2.1 is 1.4. And again, you could stop here on the AP exam. I don't think many of your teachers would be happy with that. I wouldn't be happy with it in my classroom. But there's kind of a my rules versus May rules. And in May, as soon as it's numerical, you can stop. Oops. I should have left it up longer. I'm sorry. I took that down really fast. Once you have a second to digest. So again, this was my tangent line. And this is my approximation. All right. And then part D. And again, I have this comment that it's not an AP caliber question. It has to do with some of the weakness we have. It's because I merged problems, but it says now, do you suspect this is an underestimate or an overestimate? I'm going to give you a few seconds to think about how you would explore that, maybe give you a chance to explore it. I am going to say part B comes in, or part A comes back into play. Are we going to get a visitor? I've got a cat going by. She's showing very little interest in me today. Yeah, my lighting is really goofy because you can see on my shirt, I have a window right here. And Aaron, you'll get a kick out of this. 15 years ago, when I bought a glass desk, I did not consider the ramifications of how that would affect video chatting in the year 2020. And so I have a lot of light coming in through the right that I have nothing I can do about. All right, let's go ahead and look at this. So this, whether this is an underestimate or an overestimate, well, we have a tangent line. And so we have this 0.21 somewhere on this curve, and it has a slope of 4. Right? So that's our tangent line. That's not a slope of 4, but use your imagination. The curve is living in one of two places. if the curve is doing this, then at 2.1, we have an underestimate. If the curve's doing this, then at 2.1, I have an overestimate. Now, the weakness here is the curve could do like an S-turn, right? It could look like a cube or a cube root or something like that, or a cosine wave or something, where it comes back and cuts through. So even though it's concave down at 2, it might have a point of inflection and pop up before 2.1. You know, it could have a real tight S-curve in there. So I really need to be able to check the entire interval. So when they ask these questions, they tend to have second derivatives that are only in terms of x, so that you can confirm that. So that's why this is not an AP caliber question, but I wanted to get this idea in. So we're going to bring in our second derivative, which was d squared y over dx squared. And I'm going to have to recompute that, minus 4y dy dx, which was 3 minus 4y, 3x minus 2y squared. All right. And so I want to find that at this point 2, 1. So I'm going to use a slightly, let's see. Use a slightly, by the way, I'm addicted to colored pens. I keep changing colors just for fun. At 2, 1, this second derivative, I can do it this way as well. I don't have to do that such that bar, is 3 minus 4 times 1. And then again, I know dy dx at 2, 1 already. It was 4. So this is 3 minus 16, which is going to be less than 0. And again, I could plug into this as well, or I can distribute the 4. I think I actually did it when I did it myself yesterday. I did minus 12xy plus 8y cubed and plugged into that, which wasn't a big deal because y was 1. But as soon as I can declare it's less than 0, I suspect we're concave down. And so if we're concave down, we're curving away from the tangent line below. The tangent line's above it. I suspect this is an overestimate. I can't guarantee it only because I can't speak to what's happening between 2 and 2.1, but I strongly suspect it does not change in that window. Like I said, in the AP test, it'll be all in terms of x, so you can make that call over that interval. Are there any questions coming to you in the chat yet, Aaron? Are we?
Nope, no questions.
All right, cool.
If you
All right,
do, though,
well,
please throw those out there. Mark
yes,
is not that intimidating of a person.
No, and the worst thing I could hear is, oh, he went too fast and he didn't explain something, because please stop me. Okay, let's see, Aaron, you probably recognize what this one's based on. This is another one I've written, but it's based on a past exam question. And again, there's a wall of text. Oh, that's something I wanted to mention earlier that I forgot. When you open an actual AP exam, you never see a wall of text like this on a free response. They're spread out over 2 pages. So there'd be, in the upper left, there'd be the graph with the stem, which is that part above, which doesn't actually contain a question. And then there'll be a line, there'll be a box with part A in it, a box with part B in it. So if you want to like cover things up, the way we went through the slides part by part is actually closer to what you would see on the paper than what we're seeing here. It says the function f is differentiable on the closed interval -5 to 4 and satisfies this initial condition of f of -1 equals 11. The graph of f prime, the derivative of f, consists of 3 line segments and a semicircle as shown in the figure below. And then it says, on what open intervals is f concave up and increasing? That should sound familiar from the warm-up. For what values of x does f have a point of inflection? Find the absolute maximum of f on the closed interval -5, 4 and justify your answer. And then for each of the second derivative at -3 and 3, find the value or use the limit definition of the derivative with one-sided limits to justify why it does not exist. So again, we're going to look at these one part at a time. So there's part A, and I'll give you 30 seconds, maybe 40 seconds to take a chance to look at that. Sorry about that. All right. So on what open intervals is f concave up? Actually, you know what? I'm going to do the increasing first. Increasing is a little more what we're used to doing, right? So increasing is going to be typically where f prime is greater than 0. I could actually say greater than or equal to 0. You can message me or email me if you want to know more about that. That's always a fun discussion. that's why we went open intervals here. But where's f increasing? And f is increasing from, as an open interval, from -4 to 1. It's in this, if I can get my cursor, let's see if I can get, I'm gonna have to, still on pen. So we're increasing in here, right? So when we're increasing in here, that's where my second derivative is positive. So let's see if I can come in. I tried to draw that with a mouse. That was a mistake. So that's where my second, what am I doing? Surprise, is the chat blowing up? That's not what he said. That's not what he said.
Not yet.
So, hey, here's the great thing about having 15 minutes per free response. You can catch yourself when you do silly stuff. This is f prime. We are looking at f prime. I said where f prime is greater than 0. That's everything over here. That's all right. Well, the good news is I'm not hearing tons of disconnect sounds. People checking out. All right, so f prime is greater than 0 on the open interval from -1 to 4. Again, that greater than or equal to, because we have that point at 3, which I'm not really going to worry about because it's not going to come into play. All right. And as I just foreshadowed, because apparently I was already answering the question, concave up. Concave up is going to be where f prime is increasing, or where f double prime is greater than 0 again. And so I'm going to come over here and try not to screw this up again. So that increasing interval now is this, what I had highlighted before. So f is increasing, f prime is increasing all along there. And so I'm looking for that overlap. And it looks like my overlap is right there. That's the only place where my derivative is positive. Oh, wait, there's another one. Right there. So we have 2 intervals. So we have concave up and increasing from -1 to 1 and from 3 to 4. Does that look right to you, Aaron? I shook myself on that.
Yeah, no, I think we're good.
So my apologies on how rough that was. That's funny. The problem is I decided to do increasing first and my brain was still answering the first question. So that's what I get for trying to out clever myself. Hopefully it went smoother for you guys and I just confirmed that you were right. All right, so for B, I'll give you a little time to do this, and I'm going to take a little time to look at this and make sure I get a little better job on this one. For what values of x, values of x, does f have a point of inflection? Oh, and by the way, the justification, because it did say justify on A, the justification on A was just this, where f prime is increasing, where f's greater than 0. All right. So there's a couple ways to justify it, and I actually kind of start this one with the justification because I have to know what qualifies as a point of inflection. So points of inflection, that's going to happen when the second derivative changes from positive to negative, or vice versa. And so that means that's where the first derivative changes from increasing to decreasing, or vice versa. Which is also the same as saying where the first derivative has relative max or relative mins. And any of those can be used as justification. The second derivative, you want to be careful. If this isn't given as f, if this is given as g, and g is the integral of f, or f's the integral of g, you want to make sure you make those connections of what you're looking at as the second derivative. With this, you're given f prime, so the second derivative is how this graph is changing. I would probably stay with first derivative only because I was given the first derivative and I like to stay with my primary source of data. And I'm a big fan of the relative max min version, because if I do that, now I just come in and wherever this graph has a min max, which is at -4, 1, and 3, I can see right there, I go from decreasing to increasing, increasing to decreasing, and decreasing to increasing, which means my second derivative, I think double prime, is switching from negative to positive, positive to negative, and negative to positive. So I can see those changes from concave up, from, sorry, starting at the left, from concave down to concave up, and concave up to concave down, and so on. So I would say the points of inflection occur at -4, 1, and 3. They only asked for values of x. I actually can't find the values of y. Well, I could. I can use that initial condition, but they just wanted the values of x. And the y coordinates here are the y coordinates of the derivative. So they occur at those. And my justification would be there are relative max and min, relative max and relative min on f prime at those locations. Or I could list them again. I could say at -4, 1, and 3. And again, you could also say the first derivative changes from increasing to decreasing, or vice versa at those locations, and that would be perfectly fine. In fact, that's the way a lot of teachers model it, and it's the same statement. So. Any questions on that one coming in?
Nope.
Okay. So let's look at C. C is a very common free response question. This is one, if you want to go ahead and take a shot at it, I'll give you, see, we're at 10:40, not yet, 10:48. I'll give you a full minute and a half after I get done reading on this one. But if you just want to write down your strategy as well, that's not a bad way to look at this one. It says the function f is differentiable on the, oh, that's the stem. Find the absolute maximum of f on the closed interval -5, 4, and justify your answer. So given just the derivative, can you find the absolute maximum on this? All right. Oh, I think that was a minute. Oh. I have jotted down some notes for myself on this one. All right, I'm going to bring you guys back to this. Just a couple notes I made for myself. So I'm looking at f prime. I have critical numbers at -1 and at x equals 3. At -1, we have a sign change from negative to positive on f prime. So that's actually a chance for relative minimum. And so I know it's 11 there because that was given, but that is a relative minimum. So it's really not in play for this, but I still wanted to have that information jotted down. And then at 3, there's no sign change in f prime. It goes from positive to positive. So that one's not going to be a candidate either. And actually, there is a good way to make an argument that I already know where it is. And there's a couple ways we can deal with this. The f equals -5, I can find the value, and we can find the value pretty easily. It's going to be f of -5 is going to equal f of -1 plus the integral from -1 to -5, which is going backwards, but I'm okay with that, of f prime dx. And that's using the fundamental theorem of calculus and maneuvering things around to create an accumulation model, a little foreshadowing of stuff we're going to talk about in our second hour. That -1 to 5 is just that triangle. It's this triangle right here. It looks like it goes, it's 4 wide and 3 deep. So it has a bounded signed area of -6. The area is 6, but it's below the x-axis. So the graph dropped 6 units to get to 11. So this is 11 minus -6. So f of -5 was at 17. And I can do that using the geometry, or I could write the equation of the lines, but man, I don't want to do that. I knew it was going to be higher because that area was negative. You could eliminate it by that, but it says to justify. And instead of writing the sentence trying to explain, I know the graph drops at f of -5 to f of -1, and therefore f of -5 is not going to be a candidate to be the max. I mean, it is higher. Actually, it may be the maximum, right? It may be higher. It's easier to me. This is just called a candidates test. And to me, it's just easier to go find every value of the candidates than to sit there and talk about why I'm eliminating them. That seems to be, it's harder for me to get that into words than just go ahead and find that 17. F of 4, I'm going to use that same model. I can do f of -1, and I'm going to integrate from -1 to 4 of f prime dx. So I'm going to start with 11, and then I've got to start finding some areas. Again, this is a semicircle. It has a radius of 2. So we're looking at 1/2 pi times 2 squared. And I have this triangle that's a 1/2 triangle. So that has an area of 1. So this is going to be 11 plus that. What does that end up being? 2 pi plus 1. Or 12 plus 2 pi, I suppose. And now I have to decide, what's my maximum? Well, it's not the 11 because these are both higher. And this is going to be on a non-calculator part of the exam. You actually have to be able to eyeball whether this is bigger than 17 or not. But we all know pi is basically 3. So this is a little more than 6. So this is a little more than 18. So this is going to be my maximum value. And that is your justification of those 3 points. And word of warning, if you're going to try and find a decimal to this, if you're really not comfortable with leaving it as 2 pi and you want to do 12 plus 2 times a decimal, carry more than 2 digits. Because even though it's a non-calculator part, you're going to be held to the 3 digits, the 3-digit approximation rule. So if you just used 6.28 for that, you're actually not going to get the answer point, and that's a shame. And I would just, you know, this is bigger than 6. You know that plus 12 is going to be bigger than 17. You can trust yourself on that.
We have a question.
Oh, excellent.
Someone asked, where did the f of -1 come from when doing the candidates test, and why do we include that in our value?
Okay. It came from the stem. It came from up here. It was, there's never extraneous information on these free responses. Every single piece of information in that stem is going to be used at some point. We didn't use that in A or B. It did get used in C. So even though this is going to be spread out over 2 pages and the C is going to be in that upper right, you do have to remember when you look back, is there anything I haven't used yet? The reason it's included is when I'm looking for mins and maxes, this is that extreme value theorem. The extreme value theorem, excuse me, says for a closed interval A and B, the absolute min and the absolute max occur at the endpoints or at a critical number. Oops, I need to scoot back. Let me zoom the camera out. So we were given a closed interval from -5 to 4. We know our absolute and absolute max are going to occur at endpoints, which are critical or the critical numbers. Now, this is a critical number, f of -1, is a critical number where the derivative changed from negative to positive. And I get that. So we know it's a relative minimum. It actually turns out it's the absolute minimum. And we were asked to find absolute max. But because the extreme value theorem says this, I either have to find the value so I can rule out the value as a min or a max, or I have to say why I'm not addressing it. So like 3 was a critical number, and I addressed why I wasn't using 3, because 3 had no sign change. So it wasn't a minimum or a maximum. But I did have to at least address both candidates that were interior critical numbers as well as the endpoints. I hope that answers the question. But yeah, the value came from the given information. I have to have at least one point on the graph to be able to find these values. So if they ask you to find a min or max, you're going to have a value on F. And then the second part of your question was, why did I look at it? Because I didn't want to write a sentence about why I didn't. You have to make a choice. And if you could tell Aaron whether that answered your question or not, I'd appreciate that.
Nope, they said thanks.
Okay, good. Okay, I'm going to try and get through D quick. We are actually at the end of the first hour, and we are going to give you guys a five-minute break here in a second. So I'm just going to go ahead and talk about D. Aaron, do you recognize what this one's based on?
I do recognize the word, yeah.
Yeah, the phrasing on this one is pulled straight off the 2017 exam.
Yeah.
Although I used the question, the justification part's actually off the 2009 exam. So you're asked to find the value or say whether it doesn't exist. So I'm just going to go ahead and tell you guys f double prime at -3. That is right over here. I come back to my drawing. It's right there. It's on a line segment that has a slope of 1. And this is f prime. So f double prime is the slope of the tangent. So you can actually just declare -1. You can read that slope off the graph. I don't have to show a difference quotient, although if I wanted to, I could. I could do -3 minus 0 over -4 minus -1. And but I don't have to because I'm reading it off the graph and the graph was given. So that one's pretty straightforward. You do have to remember by part D that you're still looking at the first derivative. The second derivative at 3, well, I'm looking at the derivative of the derivative at 3, and we have a corner there. In 2017, it just said explain. It didn't say justify. It said explain why the derivative doesn't exist. And students could just say, does not exist. And then if it asked for explain, they could say there's a corner at x equals 3 on f prime of x. You do want to say which graph it's on. Explain is pretty much as close as you're going to see on the AP test to say in your own words. Explain is really open for the students to write. This says to justify, I'd actually would use the alternate, what people call the alternate definition. I think it's easier. The limit is x. You could do it with what's I guess considered the main. I don't know. It's the other alternate. But I would do it. It's the derivative of f prime. So this is that y2 minus y1 over x2 minus x1 version of the derivative. And from the left side, it's approaching negative infinity. And from the right, and again, these are primes because I'm looking at the second derivative. From the right, it's approaching, what's that thing doing? Going up 4 over 2, or up 1 over 2. It's a slope of 2. And because those aren't equal, it doesn't exist. And that would be your justification. It does not exist because the two one-sided limits aren't the same. And you could do it with the x plus h model as well. I just find this one to be more intuitive for this. In 2009, the directions were exact. I typed these directions straight off the 2009 exam. They asked for this. Hopefully they'll say explain, so you can just say corner. That's much to the student's advantage. Hopefully for the readers, they say use the limit definition because that's easier than accepting 800 different explanations. But that's a very selfish reason. But I hope that makes sense. So that's, and on the 2020 exam, if any of you are looking at the digital administration, they asked questions like this on the digital exam last year, because this is something with the explain part, because that's something that's really easy to type and really hard to Google. It'd be really hard to image search this Google and say, where does the first derivative not have a derivative? So if you're looking at a digital admin and wondering, well, what kind of things are they going to ask that I can type? That's very much something they could ask. All right, I'm going to wrap up this section and I'm just going to point you at some resources and then we'll take our break. This is a very high level multiple choice question. I really like this one. I don't think they would ever ask anything like this on the exam. They've asked a smaller version. They've asked a version like this question before where they only had these 3 parts and only 3 graphs over here. And I think that's actually very fair game. But what you're trying to do here is figure out who the granddaddy graph is, and then try and figure out who the derivatives are. And I will just say my clue for this is find the zeros. Find the tangent zeros. And then look for graphs that have zeros at those points. And that really gets you going. That starts eliminating which ones are derivatives of which. So that'll get you to where if you can find those zeros on the other graphs, you can start setting them up in order. This Desmos, I set this to be open for a year. So you can do this at any point between now and the exam. I'm not going to monitor it, so don't worry. If your name's in there 8 times, I don't care. If you log in on Student Desmos and type it in, it'll save your progress. But you don't even have to log in. You can do it as a one-time thing. And I'm going to go ahead and look at it. I have it pulled up already. Oops. Trying to take over the screen. All right. And this is a matching game that just does these connections between derivatives and their partners. And I'm going to get some of these wrong on purpose. It says up here at the top, the ones that are white with red graphs, those are the functions. And the purple are the derivatives. So they have grids. I did color and I did grid and white in case you're colorblind, because I have a friend that's colorblind. So I've become very aware of that. But you just match them up and you hit next and it self-checks. And I'm pretty sure I got 2 wrong there. So it says not yet, go back. But it builds up. Then it has functions with function descriptions. You can check yourself. Derivatives with descriptions. And then the granddaddy, groups of 4. Match the function, the derivative graphs with the function and derivative explanations. And you can match those and they self-check. And that first batch, all of these graphs and expressions are in those previous slides. So you kind of have a head start. And then the last grand finale is new ones to try to do the whole thing with. And those are self-checking. You can share those with your teachers. I think, okay, I did not do it here, but I have a teacher link as well for the teachers. It's actually in my notes. And if there are any teachers here, let's see. Man, dual screens is cool until you get lost. Oh, wow. Okay, it won't let me copy and paste that out of the, it's in my comments. It's in the comments for the slideshow on this slide is the teacher link. When you shared this, did you share the whole PowerPoint or did you share it as a PDF?
It was whatever link you sent me. I think it shows up as a PDF.
Okay. If it's the Google Slides, you should be able to download it as a PowerPoint. It will be in the comments.
Okay.
If not, email me and I'll fire it off to any teacher that wants it. These are the problems that those free response we were working on were based on. Don't write these down. You can Google 2016 BC4. It'll show up. It is a BC problem. I know you're AB, but parts A, B, and C were all AB material. And the first free response was based on that. The second free response was based on the 2017 number 3. So thank you guys for that first hour. I know we're way over, but we're going to take a 5-minute break. So I have 11:07. So 11:12, we'll start the second session.
Sounds good. In the meantime, if you have any questions, put them in the chat. You can direct them specifically to me if you don't want them out in the general sphere, and I will get those to Mark, and we'll see you here back in about 5 minutes.
Excellent. And I'm going to stay. So yeah, you can definitely direct those questions. Thank you for saying you understand, because I would just keep talking. I just keep going. All right, it's 11:14. We're going. And I did get a question privately about that multiple choice question that I skimmed, that extended multiple choice. It's in the handouts. What it is a graph of f, f prime, f double prime, and the antiderivative of f. And you're trying to match which one is which. And I don't think they would ever on the AP exam ask all 4 of those, but they have asked for 3 before. So they've asked f, f prime, and f double prime, and try to put them in order. And focus on critical numbers and where the zeros would be on the derivative, and then look at increasing and decreasing intervals, and it tends to take care of itself. Okay, this one's a little flipped. We're going to warm up with a free response. And then we're going to look at some multiple choices that I wrote. So these are just kind of open-ended for you to read. And I'm going to have a little more direct instruction in this one, because I think this is stuff that isn't quite as ingrained as derivatives at this point in the year. So write an integral expression, but do not evaluate, that would find the area bounded by y equals 4 minus x squared in the x-axis. Fill in the blanks for the version of the FTC given. And there are 4 blanks to fill in on the right side. And then given the integral from 1 to 5 of g of x is 4, and the integral from 4 to 5 of g of x is -3, find the integral from 1 to 4 of g of x. And of course, those are all with respect to x, but when we read them, I sometimes get sloppy. Excuse me, my cat's trying to get in and my wife closed the door. Yeah, she came in during the break, even though it's in the 70s. It was in the 70s this week, and I think it's in the 50s today. We're still recovering from the sub-zero temperatures we hit 2 weeks ago. And our superintendent is helping to hand out food at one of the local parks, and he needed help. They were undermanned. So my wife and kids have gone to do that. So. All right. May not be enough time, but I'm going over time. So let's go ahead. Let's go ahead and talk about these. All right, the integral expression. Hopefully you don't need a calculator for that, but I'd be okay if you need to grab a calculator real quick, that's fine. But 4 minus x squared is something that I would hope after a little time you're like, okay, it's a downward parabola. It's been shifted up 4, so it looks like this. And we're trying to cover in that area. And that is a perfect graph. Sometimes there's some distortion with the digital transmissions, and especially with me going through Aaron to you. So if that parabola doesn't look perfect, I apologize for those internet bugs. But that's going to be the integral. And our bounds are going to be -2 to 2, 4 minus x squared dx. So it's top minus bottom, and my bottom curve is the curve y equals 0. Of course, that's not the only correct answer. For those of you that like even functions, sorry, I'm trying to get my screen to be steady. I could also just double either side. But if I'm not having to evaluate it, I would use the left one to make sure I don't make a mistake. And if I'm doing it and I have to do it by hand, I'm probably going to do the right hand version so that I can plug in 0 with my fundamental theorem, because I'm a big fan of 0. The fundamental theorem of calculus, we have f prime of x here. So the antiderivative is going to be f. So these blanks are f's. And then it's going to be f of b minus f of a. It's a very alpha looking a. Questions on these two? Okay. And then the third one, I think I'm going to bring my camera in for this one. I'll let you still see the second answer, but right, so there we go. The integral from 1 to 5 of g of x dx is going to be equal to the integral from 1 to 4 plus the integral from 4 to 5. And they asked a free response question on this a couple of years ago in that 2019 exam that was really kind of tricky. As a teacher, it threw me when they released it, because they gave part of this integral as a graph, and the other part was actually off the graph. It was like the unseen portion of the function. And so that was neat, because for students, it's not necessarily neat. When teachers say it's neat, that's kind of a scary thing. But it's interesting how they find ways to test stuff that we don't anticipate. I know the integral from 1 to 5 is 4. I do not know the integral from 1 to 4. But I know the integral from 4 to 5 is -3. So it looks like 7 is my integral from 1 to 4. All right. So this unit 6 is about the fundamental theorem, finding areas, and accumulation model. And I love the accumulation model. So there's your area, there's our fundamental theorem, and also properties of integrals. And so that third one is kind of it's a property of integral, but I can actually turn that into an accumulation model, which I really like. Questions on those warm-ups? All right.
We had one question. I think
Yes.
it just needs some clarification.
Yeah.
On the first part, is the area under the x-axis, like before -2 and after 2, not also bounded by the function and the x-axis?
Okay. So
I think they said they had an indefinite integral.
I get you what you're saying. Yeah. Okay. No, but it's a good question. So, and when I teach this, I always talk about the word bounded, because you always have kids. You guys are all smart kids, right? It's like, I mean, you're here because you're intelligent, whether you believe it or not. And that's just a confidence issue. And they're very good at English as well. And the correct past tense of bound is bound. It's like if someone is bound, they're tied up. You don't say they're bounded. If you say they're bounded, it means someone jumped over them. Bounded is a mathematical phrase. It's actually defined, if you look it up in the dictionary, it's one of the few times where they actually give the math definition in an English dictionary. Bounded is enclosed, completely enclosed. And we do indefinite integrals where we have open ends, but they're given as integrals. We don't say the area bounded by 1 over 1 plus x squared in the x-axis. we have to say more. We have to say if we go forever. We have to say extended to the boundaries. So for it to be bounded, I want to have a closed area. Because otherwise every graph would be like that, right? We'd have all these open intervals. If I said, if I said bounded by the y-axis, the x-axis, and the unless I say in the first quadrant and things like that. So it's an excellent way of thinking about it. I like where you're going, especially with the BC kids who get into impropers, and the rest of you if you take Cal 2 down the road. But if it says bounded like it was phrased here, we're looking for completely enclosed. But whoever asked that question, and you have to tell me, there are two things that you need to realize. You would make an excellent lawyer, and you would make an excellent mathematician, because loopholes are all about mathematical thinking. So I really enjoy that question. But if you don't like the answer because it has to be enclosed, I'm sorry about that. But all right, we're going to look at some Riemann sums with definite integrals, and I actually want to pull out of the slideshow for a second and go full screen camera, because these are new. For some of your teachers, these are relatively new type of questions. They asked these in the 80s and 90s, and then they took them off the exam for about 20 years, and then they came back in 2016. So it's a relatively new topic for the exam. And so it's the limit summation notation versus the definite integral. And so I just want to take a minute to explain how I teach it. We're not going to go through my full lesson, obviously, but the limit summation notation is that limit as the number of rectangles goes to infinity. If we're actually finding rectangles to find these areas, of the sum is my rectangles or partitions go from 1 to n. So I have n rectangles up here, but then I'm sending n to infinity of f of x sub k times delta x. And that is another way of writing this. This equals really means equals. Every time you write the thing on the right, you're writing the thing on the left. So let's just kind of parse it out. This is the height at every single rectangle. The function value is our height. That's the width of every rectangle. And so we're just doing height times width of every single rectangle. This means add them all up. So if I have 5 rectangles, I'm adding up 5 rectangles. If I have 30, I'm adding up 30. And one of the things we really emphasize in calc is if we want to get the perfect value, we go from estimates, which is many, many n, to infinite n. We're going to do all of the rectangles. So as that comes over here, this is still our height. Our width has now become infinitely thin, this dx, this instantaneous change in x. And then this is saying add up all the values from a to b. We're doing f of a plus a little bit, f of a plus a little bit more until we get to f of b. We add up all those linear heights and we add up with an area. And so it's this dimensional game of we're playing with linear and getting area. Later in unit 8, we add up a bunch of areas and we end up with volume. So it adds a dimension. But that's all this is. As mysterious as this looks, and it's got this sideways m thing going on and the limit, but it's just height times width, add them up. How many am I adding up? A real lot. So the way I break it down when I find this is I always try to find my delta x first, which is going to be how wide are my rectangles. And my rectangles are going to be the width of the area divided by the number of rectangles. By the way, I'm going into therapy on my ends because I draw U's because that stem separates. I realized how bad it was recently. So it's the width divided by n is how wide each rectangle is going to be. Then I have to figure out, well, where am I getting my point? And for these Riemann sums on the AP test, they always use the right endpoint. They use a right Riemann sum. So we start at the left endpoint, and we just add a delta x for every k. So I start at A, I add a delta x, and I find the height. Then I add another delta x, I find the height. Add another delta x, find the height. Then I take those heights, which is now f of xk, and I multiply it by delta x to get my height times width. So this is the entire game. So how that works with these problems I'll come back to my PowerPoint. I'll let you digest that for a second. I'm going to come back to the PowerPoint, and 2 of these examples are off of old course and exam descriptions. At this point, we have seen 6 live questions, I would call them. 6 questions that were written by the development committee. 2 in the course and exam descriptions, 1 from a 2014 supplement, which was, hey, here's some problems coming in the future. And then 2 released exams that we've seen Riemann sums show up on. I think that's correct. I think it's 5 or 6 we've seen. There is a twist that they did in one of them, which wasn't the same question, and that was weird. So what I do with these, especially if I'm going from the integral to Riemann, is I just do that process I just did of, I look at my width, delta x, my width of my rectangle is going to be 6 minus 2 over n. And I'm going to try and get this, rearrange my desk so I can get a little better handwriting. And that's 4 over n. So if I'm doing a multiple choice, I'm looking for delta x 4 over n. And it's going to be sitting by itself because I'm looking for that f of xk times delta x. So my delta x's in this are this column in these problems. And so I have a 6 over n and a 6 over n. So that's the student who just used b. But right now I know I'm already down to a and b as my choices. My x sub k is going to be my left endpoint plus delta x times k. And then there's my f of x. So I'm trying to plug this into. So f of xk is just going to be the square root of that. And this one didn't use the a. This one's got a missing, so the choice is C. And so far on those 6 problems they've released, they've all been this straightforward. And that's what we're banking on. In the 90s, they started disguising them. They'd simplify things and move stuff around, and it became an algebra question. And in 2016, when they reintroduced this, they also, on the development committee at ETS and College Board, they've made a conscious effort to not make it an algebra or a trait test. Algebra mistakes are going to happen, but they're trying to make the multiple choice errors calculus errors. They're not trying to lay a trap for the student that does something silly. So that's actually to your benefit. It allows you to catch mistakes and go back and say, why isn't my answer here? So that's actually really good for you. But I don't anticipate them going back to that 90s style, at least for a while. So there's a development committee philosophy change. So go ahead and try and do this one. This one is going the other direction. But what you want to do is see if you can pull delta x out of what they gave you. And if you can pull delta x out of what they gave you, see if you can figure out how it was used. And I'm just going to give you about 30 seconds. Actually, I'm going to go 20. Just because. That wasn't even 20, but when I look at this really complicated part, that has to be f of xk. I mean, I don't know what xk is yet, but that's where all the manipulation's happening. This right here, that's my delta x. So I know my interval width is 1. And so that's amazing for this problem because we have an interval of 3, an interval of 3, and an interval of 3. Now, this one does have this 1/3 here, which 1/3 of 3 over n would be 1 over n. So I'm not going to circle a yet, but I'm strongly suspicious of a. Now, if I work this one backwards, I get the 1 minus 0 over n for my delta x. X sub k would just be 0 plus 1 over nk, or k over n. And then if I plug that in, I get square root of 1 plus 3 times 1 over nk. Well, look what we have there. 1 plus 3k over n. That's it. We're done with a. And in a way, I really like these problems because once you figure out the patterns, they're amazingly straightforward. but I don't like them because the notation's intimidating. And I'm afraid that we're going to have students who don't go to review sessions like this, whose teachers did a great job teaching it, but they taught in October. And it puts 1.2 points in peril just because it's an intimidating look. All right. This is our last one of these. I'm going to give you a chance to read it and do this one. So 40 seconds to try to do this one. Which, interestingly, the final Jeopardy is 37 seconds. So there must be something scientific about 40 seconds. Oh, that's not true. The last one was from that. Copy and paste error. Okay. So how I would start it is, this one's different, right? They gave you an area, and we have seen this as well on our released exam. So the first thing I'm gonna do is I'm gonna write an integral over here. The integral from 1 to 4 of that function, which is that, the natural log of 1 over x with respect to x, would get me that area. But it would get me that area as a negative because it's below. So that's why there's absolute values on all these answers. So the absolute value is to make it positive. And then I'm going to work off of that. So my delta x is 4 minus 1 over n, or 3 over n. That takes out this one. This one doesn't have an apparent delta x. So those two are gone. My left endpoint is 1. So x sub k is 1 plus 3 over nk. And then f of xk, well, my function is the natural log of 1 over what I'm plugging in. So, and oh, let's see, that looks like b. So hopefully that demystifies those a little bit. I don't know if you guys have done circuits. If you haven't done the circuit on this, I wrote a circuit on this and I've included it in the folders with work for you guys. Don't want to give you homework from this, but I gave you homework from this if you want to do it. It's a self-checking assignment. It's fun. If you're a teacher and you're feeling nervous about these, try it. It really, I wrote it, so of course I'm biased. I don't remember writing at this point. I trick myself with it when I try to make keys for it. But I had one of the greatest compliments I got was one of my own students last year who made the comment, by the last 3 problems, it was so much easier than the first 3, just because after doing 16 of them, it's really the same thing over and over again. All right, this one's the accumulation model. I'm going to leave the problem up there. This is calculator active, as you see my little icon up there in the corner. But I do want to just talk about the accumulation model of the FTC. So if you want to work it because you feel fine with accumulation, go ahead. But down here below, I'm going to kind of talk about this. So the accumulation model starts with that version of the FTC that I had on the first page. And I did say the version because there are multiple versions. Sorry, I mean, pen difficulties. Because the traditional version of the FTC in integral form actually just has little f here. It doesn't have f prime. And it has big F on the right side. So we have a slight change here of going from little f to its antiderivative to evaluate the definite integral, to going from rate of change to the function that describes the accumulation of that change. So we're integrating a rate instead of integrating the parent, as it were. And if I solve this thing for f of b, I just add the f of a to the other side. Sorry. There's a button on my pen that does the erase, and I keep hitting it for some unknown reason. Too much coffee. So this is the accumulation model, is that f of b, now I can't get rid of it. I suffered a finger injury in the fall. For some reason, it's showing up right now. F of b equals f of a plus the integral from a to b of f prime of x dx. That is the model. These guys have to match. As long as those match, it works. So if the integral goes from 4 to 2, I'm fine with that as long as a is 4 and b is 2. It's a nice little, it creates the subtraction that I need. And then I want to throw one more thing up here from the first hour. Those are not totally unrelated. And I think that is so cool that this relates to point slope form. Because f prime is my slope. The dx from a to b is my difference in x. I have my initial value. And I just think that's so cool that linear, that tangent line approximation can keep showing up in all kinds of different forms. So with that said, if I'm doing this problem, it says let f be a differentiable function such that f of 5 is 4/10 and f prime is this function, the square root of 1 plus 2x cubed. What is f of 2? So f of 2 is going to equal, well, that's my b. That's the value I'm trying to find. I erase this. Come out with some different colors. So this is what I need. This is what I know. So I know f of 5 plus the integral. And it's from the one I know to the one I need. And that's the one thing that's a little weird about accumulation model. But I'm going backwards. I'm going from 5 to 2. So what that means is I want to subtract the change that happened from 2 to 5. And so that creates that, because this is one of those properties that by doing this, I'm actually subtracting that. So this is going to be 0.4 plus this integral. And I would just throw that in my calculator because we're calculator active. Whoops. So I've got 4/10 plus my integral from 5 to 2. Square root. I hope that's one person having internet problems and I'm just not losing the whole audience right now. And we get negative 28.205, which is choice C. Any questions about that one showing up? Aaron?
No, we seem good.
Okay. Okay. Excuse me. So this one, I'm going to read it to you again. I'm going to give you a couple seconds to figure out what you might do. It says the graph of the function f shown above consists of 2 line segments. If the function g is an antiderivative of f such that g of 2 is 5, for how many values of c from 0 to 6 does g of c equal 2? We have our choice is 0, our choice 1, which apparently has a grammar error that PowerPoint doesn't like. Choice 2, choice C is 2, and choice D is 3. Surely in PowerPoint, there's a setting where I can say, don't show my grammatical errors, double underline.
Here's another question.
No, I know what it is. It's a screenshot of my Word document. And that's what it is. And so it was the Word document was telling me that before I took the screenshot.
Here's a question that got posed.
Yeah.
Do you lose points for writing things left and right that are not equal?
Yes. Yes, most of the time. I mentioned in the first hour, if you're asked to find an estimate, and then you write the estimate equals. Like I was asked to estimate G of 2.1 in the first hour, and I did squiggle lines. But if I said G of 2.1 equaled 1.4, and I had been asked to estimate that, or if I'm asked to estimate an integral with a Riemann sum, and I say the integral equals that 3 rectangle Riemann sum, we're not going to count off for that because you're setting it equal to the thing you were asked to find. But yeah, there are, the big one is average value. I'm gonna go ahead and bring up my camera. This one is a really common one that you see, is the student's asked to find the average from 1 to 3, the average value, sorry, I'm cutting corners, of f of x, whatever f of x is. And the student does the integral from 1 to 3 of f of x on their calculator, and they get 17.684 or something like that. And then they decide, I'm going to divide it by 2. And they get the correct answer. Whatever that would be, 8.742 or whatever it is. That's not, it's 8.8, but anyway. That's wrong, because this doesn't equal half of that, and it doesn't equal the correct answer. So it's when you see these chains like this. Now, I throw 1/2 in here, we're golden, we're good, because that's what you should do, 1 over 3 minus 1. But yeah, so if you left that 1/2 off, then you don't want to do this until another line. Now you can do it on the next line, as long as they're not connected. We call it a linkage error. I'm sure Aaron knows this phrase. But when you link things that aren't equal with equal signs. But then if I said my average is 17.684 over 2, then I'm fine. But yeah, you will get, did I do that? That's the next question is, did I have an inequality up there? Because yes, it can. It's generally when you just try to say too much at once. Okay, probably had enough time to look at this while if you were looking at that instead of listening to me. I want to talk about this one because this one is the accumulation model, but it's done in a slightly different way because it's this area. And I really want to think of this one geometrically. You could write equations for the lines and work through this. But again, we have this fundamental theorem hiding in here, right? That this is f, and g is the antiderivative of f. So this is really g prime. But turn my pen off at some point. So that's really g prime. So this is how much g changes. And that's what this accumulation, this idea of accumulation is, if we're looking at a rate of change graph, the area is the accumulation of that change. So if I break this thing up and I look at this triangle right here, this triangle that's an increase of 2 because the derivative is positive, we're increasing, the total change is 2 in that window. This one is -2. This one, if you look at that line has a slope of -1/3. So I can actually figure out that has a base of 2/3 times 2 is 4/3. That actually has an area of -2/3. That's probably one of the hardest things to do on the problem. And it's not horrible. The other triangle has a base of 4/3, a height of 4. So this area is 8/3, and that means it increased 8/3. Now, the one point I was given was this 5, that g of 2 is 5. So what I'm going to do at the top here is these are going to be my g of x's. And I know g of x is 5 right here. It drops 2. So it's going to be 3 at the end of that drop 2. And then it increases 2. So it's 5 again at the end. Going left, g dropped 2/3 to get to 5. So this was at 5 2/3 before it dropped. And then it increased 8/3, which is also 2 2/3. It increased 2 2/3 to get there from g of 0. So g of 0 is 3. So this graph starts at 3, increases to 5 2/3, drops to 5, continues to drop to 3, and then increases to 5. And so by intermediate value theorem, or actually more than that, I know it never goes lower than that. So it never hits 2. And so the correct answer is 0. But I could use the intermediate value theorem. If I ever got below 2, I could guarantee crossing it. So that's a pretty cool problem. That was actually written by a participant in one of my workshops. And I was really proud of them for that. And very thankful that I have permission to use it. Okay. This one, I'm going to change the directions because we have 12 minutes left. It says at 10 p.m., rain started falling at a rate of 3/2 e to the negative 1/10 t, where t is the time in hours since the beginning of rainfall. Which of the following expressions gives the amount of rain in inches that falls from midnight until 3 a.m.? Go ahead and just try to get the integral expression that you would evaluate. Instead of trying to get all the way to the answer, just see if you can get the integral you need to find this answer. And oh man, I forgot we had the poll ability. We should have thrown the poll up on that last one. Of course, we're not going to do poll on this one because I don't necessarily want you finishing it.
Yeah.
We'll do poll on the next one.
I don't know how fast you can come up with 3 distractors for.
Yeah, I know yeah. I thought about it, but yeah, I don't want to play that game. I will say, if you already think you have your integral, I am going to point out a couple things. We have 10. For Aaron and any teachers in the room, those 3 choices were inspired by the banana problem. All right. So the easy part, or hopefully the easy part, is we're going to integrate r of t, which of course is the integral of that expression if we want to do that. The harder part, the trickier part on this is the bounds, because this equation starts at 10 p.m. That's t equals 0 for this expression. So where's midnight? And so my lower bound is 2. And they did this on the banana problem where they had, when the store started to restock bananas, it was like 3 hours after the store opened. And so you had to adjust that integral. And then 3 a.m. is not going to be 3, because 2 to 3 would be 1 hour. That's a 3-hour window. 3 a.m. is 5 hours after 10 p.m. So you're going to do the integral from 2 to 5 of r of t dt. And that's because t is the time in hours since the beginning of rainfall, which was 10 p.m. This is not a trivial antiderivative. You do have to pull this. The way I do it is I pull the 3/2 out. And then I realize I need a negative, I need a negative 0.1 for my chain rule. That you could also do it as a u to u substitution. I think that's how most people do it. And then to offset that negative 1/10, I have to multiply by negative 10 in front. And that first number ends up being a negative 15. That actually reduces the number of choices really quick. This 0.1, this negative 1/10, it goes away for the same reason it shows up when you take the derivative. When you take a derivative, chain rule comes out. Antiderivative is the inverse. You need a chain rule to get sucked back in. And that's what u to u substitution does for you if you do this as a u to u. And then you plug in 5. And I believe nope, it's not that one because it has a negative 5 in front. It's that one. You get negative 5/10 when you plug in the b and negative 2/10 when you plug in the a. All right, this one's a little more straightforward. It's a calculator active. And let's give you a minute to read it, throw that in a calculator. You can use Desmos if you're online. And then I'll have Aaron throw up a poll.
All right, I'll go ahead and put the poll up for people as they
Yeah,
finish.
thank you. Appreciate it. I can't explain what a luxury it is to drink out of a coffee cup while teaching, because I've been teaching in a mask since August because we have people in person and people online. And so I've been drinking my coffee out of a straw, which is weird. All right. Oh, that's interesting. You and I aren't eligible. I just noticed that the number of people eligible to vote is 2 less than the number of participants.
Yeah, that's right.
I was like, oh, 2 people left. And I was like, oh no, Aaron and I can't vote. All right, let's go ahead and start talking about this
All
one.
right.
I'm going to pull my camera up for this one in a second, but so you have the initial condition 67. So we're definitely going to use that 67 because we're starting with that much. And then we're adding and subtracting. So this is what we typically call a rate in and a rate out problem. And I apologize for you staring at the top of my head all the time, but I folded my laptop flat to help my handwriting. So I'm going to add the water that I'm putting in, and that's the integral from 0 to 3 of E of t dt. And then I want to subtract what's leaking. So we're going to subtract the integral from 0 to 3 of L of t dt. Lost my camera. There we go. So, zoom in a little bit so you can see my screen. Maybe brighten that up. Okay. So 67 plus, and then if I want to do this kind of hard on myself, I'm gonna do the E of t, which is 8x, because I didn't change my variable, sine pi x divided by 6. And I can do it as one integral. Since they're both 0 to 3, I'm just going to go ahead and do it as one integral minus. And this is just something because this was a couple of years ago they added this. And if teachers don't know this, this is so cool. If you just hit alpha x, that's the fraction shortcut now. Alpha x brings up the fraction template on the color 84s. And I'm going to do that with respect to x. And we get 90.365. This is not how I would recommend doing it on the AP exam, typing it in like this. I think there's a lot of places to make mistakes with fractions, especially. I actually put these into Y1 and Y2. This is going to be part of a bigger problem usually. Generally, this isn't going to be a multiple choice. It's going to be a free response. So I put E into my Y1 and L into my Y2. And then I just integrated Y1 minus the integral of Y2. And those Y2s, again, if you have the color 84s or the black and white 84s, if you do alpha F4, that brings up a Y menu, and you can just grab your Ys from there. And that's really handy to be able to do. If you have an 83, you can get there through the variables button. I'll leave that as some exploration for yourself with the internet or your teacher, or fire me an email. I can send you a screenshot. If you forget it's F4, you start on F2. As soon as these tabs are here, these buttons are just tabs, and you don't have to hit alpha again, so you can get over to the Y variable that way. So that's just handy. And on the AP test, if it was a free response, you're allowed to write it the way I wrote it here. E of t and L of t are named functions. You can write them in there. You don't have to use 8t sine of pi over 6t and 4t squared over t plus 4. You can use the names that they were given in the problem. All right. This is actually our last problem. It's noon. do you want me just to tell you what resources we have and leave this one?
You can go a few extra minutes over if you're wanting to.
I'd like to do this one because this was based on a released exam, and this one is really weird. So I probably should have put it earlier. I know people are going to be leaving because you've got scheduled time, and I totally understand. You can watch the recording later, but I'll just go ahead and do this one because this one, if you don't know how to get started, it's bizarre. So you're given this graph of a continuous and differentiable function. From the interval 0 to 8, the integral of f of x is -68. But the total area bounded is 466. Find the integral from 2 to 3 and the integral from 6 to 8. So what you have to look at is the integral from 2 to 3 and the integral from 6 to 8 have something in common. And Aaron, I'm going to let you be the voice of my teachers and students. What do those two have in common? Those two intervals.
Um,
And I didn't tell Aaron I was doing this.
They're both below the x-axis?
They're both below the x-axis. And that makes a difference when we look at total area bounded versus just the integral. Yeah, this is like the worst thing my kids can hear in class is, oh, this is a cool problem. Then they know, oh, it's one of those. So the integral, we were told the integral from 0 to 8 of f, and I'm going to leave the of x off. I'm just going to integral of f is -68. Well, that's the integral from 0 to 2 of f plus the integral from 2 to 3 of f plus the integral from 3 to 6 plus the integral from 6 to 8. Sorry about the focus level here. Get this out a little bit. And I'm told the total area is 366, 466. Well, total area is the absolute value integral. And that's going to be the integral from 0 to 2 of f minus the integral from 2 to 3, because it's the opposite of the negative, plus the integral from 3 to 6, minus the integral from 6 to 8. Because we have to subtract those negative areas to make them positives. And that is an amazingly high-level property question to throw on a multiple choice test. But what they've created is a system. And I want to know, and I know I've got the problem covered up, they want to know this one plus this one. And you can't see my arrows there. They want to know what those two added together are. So I want to get rid of these parts. So I'm actually going to subtract these equations. And this is why it's calculator active. -68 minus 466 is -534. 0 to 2 integral minus 0 to 2 integral is 0. Integral from 2 to 3, subtract the opposite of the integral from 2 to 3 is 2 times the integral from 2 to 3. These are going to be 0, and these are going to be 2 times the integral from 6 to 8. And if I divide the whole thing by 2, and again, I'm using a calculator for this, just off screen. The integral from 2 to 3 of f of x plus the integral from 6 to 8 of f of x with respect to x is -267. This was on one of the released practice tests, the ones that were actually written as a practice. So we don't know if this has been on an actual exam yet, but those are written by the same people. And I just think that's like, wow, because the only way that I ever would have got this problem right is I just started writing. Like, I didn't know what to do off the bat, but I knew, wait, total integral, I'm just going to add the areas. Absolute value, I've got to deal with those negatives. And I just started writing stuff. And then I realized, oh, wow, they're asking about the two that are in common. And so my AP Daily videos, I almost always end with the phrase, keep your pencil moving. And this is why, because I could stare at this for a half hour and not have that occur to me. But as soon as I started writing the expressions, then I was like, oh wait, I need to get those together. And some of you might be brighter. Some of you might have read been like, oh, just subtract them. But subtract them and cut it in half. But that is such a cool little problem. And realize I picked this problem to expose you guys to it. This is a rarity. This would be like one of all 45 multiple choice would be this difficult. Like, don't think on May 4th, oh God, I got to be prepared for all these things. But it's 1.2 points that you might get that someone else might not if you're prepared for it. So I do have a circuit for accumulation as well. If you haven't seen circuits, have I got a treat for you? Gonna pull. This is the Riemann Sum Circuit. What these do, the way you do a circuit, is this answer is the answer to another problem somewhere in the circuit. So this says find a limit. So you're going to write that limit summation for this thing. So delta x is 4 over n. X sub k is 4 over nk because I add that to the 0 and I plug it in. And then you go find the answer. Now I made these harder than they're going to be on AP because I didn't want you to be able to cheat. That one is actually this one. This is that thing expanded out. So this is my number 2, and I write number 2 here, and then I do this problem. And it takes you through, and when you get to number 16, number 16's answer will be this definite integral. And then the accumulation one is more calculator active. It starts off very abstract. F of 2 is 5. F prime of x is this function x plus sine x, find f of 4. So I take 5, I integrate from 2 to 4 this, find my answer. That's number 2. The very last one in this circuit is answer 101 and brings you back here. If you come back here and you still have blank problems, you got one wrong somewhere along the way. If you can't find your answer anywhere, you've done something wrong, or there's a simplification. So those are both provided with those bit.ly links. I'm sure I also gave the documents to Aaron, so they'll be in that folder with that bit.ly that he shared. Feel free to email me with questions on them. And that's it. That's what I got for you guys today. So thank you for those of you that stayed with me past noon. I appreciate it. Thanks, Aaron, for inviting me to do this. It's always fun to interact with different people, even if it's via texts.
Yeah.
I had a Q&A listed on the agenda. If anyone has some questions they want answered, my family went to hand out food, so I've got some time if anyone wants to stay.
All right, let me throw up my screen really quickly. If you've got questions, feel free to put them in the chat, and Mark will see those. Again, just a little bit of follow-up information there. Our contact information is on the screen for Advanced Kentucky. Myself and Mark, shoot him an email. He said that he welcomes all questions. Reminder, handouts and recordings are at those bit.ly links right there. April 24th is our 4th content review session. It'll be covering integration techniques and differential equations with Verge Cornelius, as Mark alluded to at the beginning. So hopefully everyone can return, tell your friends, tell everyone to show up. But again, Mark, yeah, we definitely appreciate your time. We know you're a very busy fellow right now.
Hey, I appreciate that.
All right, and if not, I'll say good afternoon to the rest of you all. Go out and watch Kentucky lose their next basketball game, and
Michigan State's playing Michigan. Don't remind me.
it's the second run, right? They played already.
Yeah, we took a 19-point beat the other day, bro. So